here? So I'm going to do something really nice that we do in math quite a bit. I'm going to just rewrite this like this, and this is just to be awesome, okay? Look. Do y'all agree that that's the same thing? Is that the same thing? Right? I just introduced a magnitude of A and divided by magnitude of A. So these are really gone, right? But now what's the top? The magnitude of the cross product, right? So this can be rewritten as the magnitude of the cross product of those vectors over the length of the vector A. And now you have a formula for D that requires no information about theta. Pretty cool, right? So if I want to know this distance, all I need to do is take this vector, cross it with this vector, find the magnitude of that answer, and then divide it by the magnitude of that vector, and that will be the distance. It's hard to convince yourself geometrically that that's the case, but this doesn't lie, right? This is just pre-cal, right triangle trigonometry, and then this was just being really clever and seeing that I could kind of use this if I had the A here, right? If I had a magnitude of A here, I could use that, so I introduced it and divided by it at the same time. All right, so that's what this note says. At the end of the day, boom, 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 and then we have our formula. Very, very simple formula. All right, here we go. Find the shortest distance between that point 3, 6, negative 7 and the line that goes through those 2 points. So I have this point here, 3, 6, negative 7. Then I have a line that goes through the point 0, 3, 5, and the point negative 4, 9, 10. And I'm trying to find the shortest distance between that point and that line. So I'm trying to find this right here, D. And remember, we're not on a flat sheet of paper here, right? This is arbitrary. This line's just going through three-dimensional space. The point's somewhere out here. And we're just kind of looking at it from a perspective where it looks like that to us. So I need to find two vectors, right? This is the other formula we're about to use. Little d is the magnitude of the cross product of A and B over the magnitude of A, right? That's what d is. So we need the A and B vectors. Do you remember from my formula what the A vector was? The vector on the line. Hey, if someone had given me this, let's just say someone had given me this. That's the vector equation of a line, right? Instead of giving me 2 points, what if I had been given this? Could you tell me what A is? Or what A could be? What? Who said yeah? Yeah, what?
What A could be?
Yeah. See, because A here is going to be, for us, A is going to be the vector that goes from here to here, right?
Yeah.
Which is a vector that is on this line, like parallel.
Yeah.
So if instead of giving you 2 points, you were given this, could you give me a vector that runs on the line?
Yeah.
What?
Negative 3.
-3? -3, 1, -3. See, you could get, A would just be the direction vector. You see that? It would just be the direction vector. Because this A vector is any vector connecting 2 points on your line. And your direction vector definitely connects 2 points on your line. So this is almost easier if you get this, because your A is just the coefficients off the T's. That's not what we were given here. We were given 2 points, so we actually have to calculate this vector. So this vector that goes from here to here, could I go the other way? Yes, it doesn't matter. This is A, and so for us, A is what? Let's see. -4, 6, 5. Okay, that's our A vector. And then we need what? The B vector. The B goes from, the vector that goes from any point on our line to the point we're interested in. So how about we go from here to here? Let's use that one. We could have gone from here to here, but I'm just going to go that way. So what's our B vector? 3, 3, negative 12. Okay, there we go. So now we're ready. I mean, all we have to do is calculate this and we're done, right? We've got A, we've got B. So let's do this one piece at a time here. First, let's do the cross product. A, we're going to cross it with B. So to do that, I'm going to do the whole I, J, K thing. Put my two vectors. Let's go negative 4, 6, 5, over, not over, sorry, and then 3, 3, negative 12. Does it matter what order I do these in terms of this formula?
Yes.
Cross product order does matter, right? But I'm not looking at the cross product, I'm looking at the length of the cross product. So remember, if you change the order of a cross product, what does that do? It changes the direction of the vector, right? The cross product is a vector. And so if I do the cross product opposite, the vector goes the other direction. But we're looking at the length of it, so it really doesn't matter what order we go here, all right? Okay, this cross product is, let's see, I'm going to go, oh, yuck. Negative 72 minus 15, negative 87, sucks. Minus, okay, cover up the middle one, 48, take away 15, 33, and then change the sign, right? So 33, we're going to change the sign. And then and then last one, negative 12 minus 18, negative 30. There we go. Negative 87, negative 33, negative 30. I mean, maybe you change those all to positives, but I don't think we can scale that at all. Y'all all right?
Yeah, you can. Yeah, you can do it by 3.
What goes in there? 3? Oh. Anything more? No? Let's scale it then. We're going to scale it just to make our lives easier. Let's scale it. Wait a minute. Hold on. Can we? Hold on. Can we? Hold on. What are we trying to do? We're trying to find the length of that cross product, right? So if we scale it, we're going to change its length. So because of what we're doing, we can't scale, right? Because of what we're trying to do. If this was just A cross B, then if you're trying to find, like, let's say a normal vector, then it doesn't matter. You can scale it. It would still be normal. But here, we're interested in the length of this vector. So we don't want to scale it, right? We don't. So unfortunately, we're going to stick with that. And then the length of A. So I'm going to write it out here, and then I hear a calculator being brought out here. But we're going to do, the computation we're about to do is this. The distance is, okay, the length of this vector, right? The square root of negative 87 squared plus negative 33 squared plus negative 30 squared. I could have made them all positive, though. That I could have done, because that doesn't change its length. It just changes the direction.
How many digits do you want?
Pardon me?
How many digits do you want?
2, 1, 1, doesn't matter.
98.
98?
Yeah, it's 97.7.
Okay.
Or 97.8.
So A was, this was A, right? Yeah. Okay, so negative 4 squared plus 6 squared plus 5 squared. There we go. So it's the length of the cross product divided by the length of A. You said that the top one was what? Or did you do it all?
97.8.
So this is about 97.8 over, you do that one yet? Huh? Root 67? Is that what you said? Root 67? And then we could get that.
8.2 then on the bottom.
8.2, so 97.8 divided by 8.2, which is whatever, okay? You'll get the idea? I think the big thing is that, look, to find the distance, the shortest distance between a point and a line, again, doesn't require that much. It's just some, vector stuff. Everything all right?
It's root 77, not 67.
Root 77. This is 77? Okay. Thought I heard 67. Okay. That's it. So take a look at your exam 2, mini exam 2 that I just handed out. Everyone have a copy? So this is due on the 25th, which I believe is a Monday, at the beginning of class. I am asking that you work alone on this one. So I do, the other one I said, yeah, you can talk to each other, whatever. This one, I want to see what you can do. And more importantly, come to me if you need, if you want me to go over something with you. We can sit down and talk through these problems. Show all your work, right? Justify your step, justify all your answers. Look at the first one. Find the equation of the plane. Boom, right there. You know that your answer needs to be something like ax plus by plus cz, right? Something equals 0. Like, you're looking for the equation of a plane. What do you need to find the equation of a plane? There's a couple of things you could do, but what are the main things you need for the equation of a plane?
You need a point.
A point and a normal vector. That's it. So you're trying to find a point and a normal vector, right? Okay, but what is it about this plane? Find the equation of the plane that contains the point of intersection of these two lines. So remember, we need the equation of a plane, right? For a plane, we need a point and a normal vector. I'm telling you that the plane contains this point, which is the intersection of two lines. So you have two lines that come together, right? And you have a point. That point is on your plane. That's the first thing I'm telling you. Second thing is that, I'm going to read it from the beginning again. Find the equation of a plane that contains the point of intersection of those two lines, which is also parallel to this other plane. So the plane you're looking for must contain the point of intersection of those two lines, and the plane you're looking for must also be parallel to this other plane that I'm telling you. That's all the information you need to solve the problem. You have to put it all together, right? But the big takeaway is that for the equation of a plane, you need a point and a normal vector. Can you find the point? Can you find the normal vector? If you can, you're done, right? So I suggest trying to sit there and okay, I've got two lines, they intersect, I've got this plane, right? Try and visualize it. All right, number 2, find the equation of a line. Boom, right there. Find the equation of a line. Okay, that means the r equals r naught plus tv, right? You're going to need a point on the line and a direction vector. Well, I already give you a point, right? Right off the bat. Find the equation of the line through a point. I already give you a point. So what's the only thing left? You need a direction vector of this line, okay? But it has to satisfy these things, right? This has to be parallel to this one plane, and it has to be perpendicular to this other line. Okay, you'll have to think about this. Okay, number 3, find the shortest distance. Hey, this has to do with what we were just talking about, right? Shortest distance between what? The center of this quadratic surface to the line of intersection of the plane of these two planes. Okay, shortest distance. The hint here is, well, it's going to be one of those two formulas, right? Depending on whether or not it's from a point to a plane or a point to a line. Number 4, all right, we haven't really talked about 4 yet. Number 5 we haven't talked about. But you can definitely do the first 2 right now. The third one, I need to talk about what we're going to talk about now. All right, here we go.
Going back to the first one, though, parallel just means it's scalar, right?
Parallel what?
Just means it's scalar. It's.
Well, are you talking about parallel lines or parallel planes? Parallel vectors, what are you referring to?
Well, it says, which is also parallel to the plane, which means it's going to be the scalar of that plane, right? No.
What's going to be a scalar of that plane? I'm not sure what you mean by what's a scalar.
The equation of the other plane that we're looking for. So the first one says they're finding the equation of a plane. Gives us, the lines intersect. But it also has to be parallel to this other plane, which means it's going to be scalar, right, or no?
I'm not going to answer that in front of everybody right now. I'm going to because I want you to think about it, and then we can talk about it.
Okay.
Yeah.
Gotcha.
All right, good? Let's get moving on with the next section. So this next section is actually one of my least favorite in the entire class because there's not a whole lot of, I just got to show you a bunch of shit, okay? I just got to show you a bunch of stuff, and then it's a lot of things to show you, and at the end we do a couple of problems, but really it's just, I mean, this puts me to sleep, all right? So hang in there, all right? Hang in there. The concepts are important, but it's not like you have to memorize all this stuff, all right? You just need to kind of know a little bit about certain aspects of these things called quadratic surfaces and cylinders. And I'm going to make it even harder for you by turning off the light a little bit because we need to be able to kind of, let's go there. Good night. Good night. All right. I'm going to be sitting here. This is why I hate this because I'm not going to be writing a lot at all. I'm going to take, can I take this one? I'm going to sit down so I can. All right. Okay, so first things first. In two-dimensional space, right? Two-dimensional space, if we see this equation, x squared plus y squared is r squared, I hope that we're all comfortable with the idea that that's a circle, right? And so in two-dimensional space, that's all it is, right? So in two-dimensional space, we have two variables. One of them is squared, right? We're adding to it the other variable squared, and then that's equal to some number squared. That's the generic form of a circle in 2D. Wonderful. Still in two-dimensional space, if instead we have that variable squared, and we divide it by a number, and we add to it the other variable squared, divide that by a different number, and set that equal to 1, then we don't have a circle anymore. We have an ellipse. So ellipses look like this, right? So specific examples, I'll put these over here. So like in two-dimensional space, for a circle, x squared plus y squared is 4. Oops. X squared plus y squared is 4. Ellipse, x squared over 4 plus y squared over, doesn't have to be a perfect square on the bottom, 3 equals 1. That's an ellipse. How do I know? How do I know that's an ellipse? Because I have the sum, I've got my variables squared, they're both being divided by numbers, and it's equal to 1. That's how I know it's an ellipse. All right? And to figure out like how tall it is and how wide it is, what we can do is pretty simple. If you want to know how tall it is, remember the x and y axes go through like this. If I want to know how tall it is, what I do is I set x equal to 0, and I can find these 2 points. So if you set x equal to 0 here, right, then you can solve for y, and you'll get 2 answers, positive and negative, and that'll give you your top and bottom point. If you want to know how wide the ellipse is like this, you find those 2 points, you set y equal to 0, set y equal to 0 there, and solve for x, and you get 2 answers, right? Okay, so that's circles and ellipses. Where's my... In two-dimensional space. What are some characteristics here again? We've got 2 variables. In both of these, there's 2 variables. They're both squared, and there's addition between them, right? Okay. What if we change it, and we have the 2 variables in here. They're both squared. They're both divided by a number. It's equal to 1 still, much like an ellipse, but we change it to a minus. That one small change of a subtraction between them changes the graph completely. We no longer have an ellipse, we have a hyperbola. These are called your conic sections, right? So again, we're not trying to memorize this, but we're just trying to, hyperbola is x squared over, let's say, 9 minus, that's y squared over, let's say, 4 equals 1. So only difference between these two, ellipse and hyperbola, is the plus and the minus. Changes completely what happens, right? Okay, now let's step into three-dimensional space. So here we had these were all what we call quadratic or conics. These are based on quadratics because both our variables are squared here, squared. It's just whether or not we have addition and subtraction and whether or not this side is 1 or if it's some constant. When we go into three-dimensional space, now we have 3 variables, right? X, Y, and Z. So all 3 of those could appear in some equation. We've already seen one surface, right? We've seen one surface in this class that has an equation with all three variables, and that's a plane. A plane, is like x plus y plus z equals 1. That's a plane, yes? Has a normal vector. But what if some of the variables are squared, right? What do we get? So we're going to look at them. In 3 dimensions, right? In 3 dimensions, equations involving the variables x, y, and z, not necessarily all appearing together, are surfaces. So anytime you have an equation that has x, y, and z in it, and you're looking in 3-dimensional space, you're going to be looking at a surface, not a solid, a surface. All right, before computers were available to us, mathematicians had to try and graph these by hand, which is a real pain in the ass. They would do these things called traces to do it. I'm not real big on traces in here, just because we have computers and it's readily available to all of us now. So I will show you some traces, but then I'll be like, yeah, we're not doing that, all right? Okay, so let's look at our first type of quadratic surface. The first type of quadratic surface that we're talking about are cylinders, all right? Cylinders. And I want to show you the algebraic version of a cylinder right here. This is the algebraic version of a cylinder. So we're in R3, cylinder, and it has the form x squared plus y squared equals c squared. So this is very much like a circle in 2D, right? But instead of r squared, I'm putting what? C squared. So a specific example would be something like x squared plus y squared equals 9. Right? So in 2-dimensional space, this would be a circle, right? In 2-dimensional. But in 3-dimensional space, what is it? It's a cylinder. Yes, if you look at it from the top, right? If you look at it from directly straight down, it'll look like a circle in 2-dimensional space. But it lives in 3-dimensional space now, so that cylinder actually punches up through, like running parallel to the z-axis. So what we say here is that z is free. Z is free. So let's look at it this way. Let's take a point here, okay? What if I tell you that that point lives on this cylinder? Do you all agree that it's going to have some x coordinate, some y coordinate, and then the z maybe there is 8? That these two have to live on that circle, right? They have to satisfy this equation. So they have to live on the circle, but we just move that up 8. And we do that we could have changed this to anything we want. 6, and then it would be the point that's here. Or we could make it 2, and it would be the point that's here. So there's like this line that goes down, and then there's this circle in the xy plane. That's this circle back from 2D. It's just we're now allowed to extend that circle up and down wherever we want. And it creates the cylinder. I think everyone handles that pretty well, yeah? Is this the only thing we could have, though? We have x and y both being squared, added, equals a number, but we have 3 variables now, don't we? So couldn't I do this? X squared plus z squared equals 9? What would that do? How do you mean shift to the y-axis? So what variable is free there? The y, which means you're going to have a cylinder, this means you're going to have a circle. I get to use this. This means you're going to have a circle in the xz plane. So here's x, right? Here's z. We have a circle in the xz plane of radius 3, but the y is free, so it goes out this way and out this way. So you have like a beer can laying down, going this way, that way. As opposed to the first one, which went up like this, right? Circular, up and down. What else could we have? Y squared plus z squared? And then in that case, your x is free, right? So now your can goes down the x-axis, like this. Circle is in the yz plane. And that's what the rest of the notes here show. Like, okay, you could have going down the other axis or the other axis. Yes?
What does c tend to represent?
Any constant?
No, it's good.
It's just like the R was here.
Okay, got it.
Yeah.
Okay.
All right, those are cylinders. With cylinders, you always have 2 of the 3 variables appear. They're both being squared, They're added together and it's equal a number, right? And one of the variables is free. Next one is something called a parabolic cylinder, which sounds way more complicated than it actually is. It's just a parabola in three-dimensional space now. So remember the equation of a parabola, right? Like the generic parabola, most basic one? That looks like this, right, in two-dimensional space. Can you imagine that now in three-dimensional space, where you can now vary, z is free to be whatever it wants? What does it look like? It's like a taco or something, right? Like this infinite looking, something like this. You see? Like looking down from like that, it looks like a parabola, but it can go down the axis, it can go down. Well, in this case, let's see. What do I have here? This is x. Yeah, that's z equals some number in front of x squared.
Sir?
Yes?
Why is it important to know which variable is free for these cylinders?
Why is it?
Yeah.
Because it tells you which axis the cylinder is going down. So this right here is a cylinder that when you draw it, since x, y are here, that means in the xy plane, it's a circle, right?
Yeah.
And then the z is free, so that circle goes up and down. So the cylinder looks like this, as opposed to being turned on its side and going this way.
Yeah.
Is that what you're asking?
Yeah. How will we ever deal with it in this class where the cylinder is going like this, where it's not bound to an axis?
Oh, you mean that it's not like vertical or horizontal?
Yeah.
That could happen, yes.
It can happen, but will we be dealing with that in this?
Well, we'll be dealing with, this is our first introduction to surfaces in three-dimensional space. These are like the basic ones, right? We want to be able to handle pretty much any surface. But these are the ones that are like the foundational ones. Like we need to know these, know what they look like, know how to look at the equation and say, yeah, I think I know what that looks like. Okay, so if we have z equals, I'm going to run out of room here. If we have z equals, I'm going to give you some examples here. These are called parabolic. I'm just going to put para-cylinders. Then we have z equals, we could say something like x squared, right? That would be, what would that be? Z is x squared. How do I visualize that? Where does that parabola live? In what plane? The xz plane. So here's x, right? Here's z. We have a parabola just like this. But your y is free, right? Your y is free, which means that parabola can move down the y-axis this way or down the y-axis that way. So you got this folded paper, okay? We could also have what? Z equals y squared. Now that parabola lives in the yz plane. So your parabola is this way now. And it's free to move down your x-axis back and forth. What else could I have? Y equals x squared, right? So now that lives in that parabola lives where? Yeah, hold on. So this is x, right? This is y. So that parabola goes like this, and it's free to go down the z. Well, let me put it back, because this is really where it was, right? So it's like this, up and down. What else? Okay, let's stick with y first. Y equals z squared. And then there's two more, right? What? X equals y squared and x equals z squared, right? There's all these folded papers. So before class, I went to that GeoGebra, right? And I had GeoGebra do all the combinations for me. And it just looks like a complete cluster, you know? I mean, those are all those folded things in there, right? But it just shows you, I mean, there's a lot of these, right? With the cylinders, there's really only three cylinders, right? You got that one, that one, that one, right? And as long as we're not tilting them, just like running them parallel to the axes. All right, You ready for the next one? Like I said, this is real, but we got to go through it. The next one, this is all those different cases that we just went through. Okay. Next one is called an ellipsoid. Ellipsoid. Look at the equation of an ellipsoid. What does it look a lot like? Does that look familiar to you? Yeah, if we take out the z part, that's just an ellipse, right? Yeah, but now we have the z part. So what do you see here? All three variables are in this equation. All three, right? All three. So we don't have any free variables here. All three of them are squared. There's addition between all of them, and it equals 1. If I change the a, the b, and the c, what do you think that's going to do to the ellipsoid? Squat it, stretch it, right, in different directions. So I can change my a, that'll do something. I can change my b, that'll do something. Change my c. You know, it's like this weird egg. It's not a perfect egg, right? But we can change it in different directions in both, stretch it in the z or the x or the y, just by controlling the a and the b and the c. Now, see these red things? Those are what we call those traces, right? Before computers were around, what people did to draw these is they took the equation and then they would fix one of the variables. So, for example, if I use the equation, I'm going to go off the board. I hope that's all right. And you know what? Let me turn one more light on. This is putting me to sleep. Let me turn one more light on. Okay. So for an ellipsoid, if, as a generic example, x squared plus 4, x squared over 4 plus y squared over 9 plus z squared, how about over 1, equals 1. That's an ellipsoid, right? What you could, before computers to graph these, what they would do is say, okay, let me let z be 0. Let's let z be 0. If I let z be 0, what equation is this? An ellipse, right? So what I do is I go to z equals 0, and I would draw the ellipse in the xy plane. And that's what one of these red ones is. And now if I change z, let me now let z be 1, let me let z be 1 now. What would happen if I let z be 1? It would change the ellipse, right? This would be a number now. I'd move things around. I would have to divide through. I would have to have a 1 over here, so I'd have to scale this. It would change these two numbers, which would change the shape of the ellipse, but it would still be an ellipse. And if z is now 1, what I'm doing is I'm coming up 1. I'm drawing a new ellipse. And I let z be 2, and I go that and draw another ellipse, and 3, and draw another ellipse. And I keep doing that, and I get what are called these trace curves. And if I do enough of them, I can imagine what this thing looks like. Right? That sucks. That sucks. And you know how I let z be 0, z be 1? I could have done let's x